Unit 4, Day 3. We are starting Chapter 16, Random Variables. A random variable is a numerical variable whose value depends on the outcome of a chance experiment. For example, how many heads do we get if we flip 3 coins, or the length of a pencil? Okay. A random variable is discrete if its set of possible values is a collection of isolated points on the number line. So, for example, the number of heads if we flip 3 coins. And so you think about it, you could have 1 head, 2 heads, 3 heads, or 0 heads. Okay, so that would be 0, 1, 2, or 3. So this is discrete. The other one, okay, a random variable is continuous if its set of possible values includes an entire interval on the number line. So for example, with this pencil, okay, the length of a pencil, maybe it's anywhere from 1/2 of an inch. I guess, well, it could be way smaller than that. Well, we'll say 1/2 of an inch to 12 inches long. It's one of those novelty ones. Okay, and so it could be anything in here, so it's continuous. Here's some other examples. Shoe size, okay, that would be discrete because they come in 5, 5.5, 6, while foot length would be continuous because it's a measurement. Again, age, which one would that be? That would be continuous because you could be 18 years old, 1 day, 3 hours, 2 minutes, 4 seconds, 12 milliseconds, versus number of birthdays you have, that is discrete. Okay, and then we have what's called a probability distribution. A probability distribution, or probability model, of a discrete random variable lists the possible values of x and their probability. This is usually done in a table, probability histogram, or a formula. So here's my example. X equals number of heads in 2 flips of a coin. So we list the sample space, which means all the possibilities. We could have head, 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 tail, tail, heads, or tail, tail. That's my sample space. Okay, and then we could list the probabilities. Well, what's the probability of getting 2 heads? Actually, the way I should write that, since x is the number of heads, the probability of getting 2 heads is 1 out of 1, 2, 3, 4 possible outcomes. Okay, so it is 1 in 4. The probability of getting 1 head, that's this one and this one, that's 2 out of 4, or 1/2. And then again, the probability of getting 0 heads is 1/4 as well. And these should always all add up to 100%. So here is the probability histogram, and I actually drew it as a bar graph. I didn't connect them because it's discrete. If it was continuous, then I would want to close the gaps. Notice that this almost looks like, or is, a normal model, where this would be mu. Okay, and that's not always the case, but in this case, it is. Okay, and notice that I have the x-axis labeled with the random variable, which is the number of heads, and the y-axis from 0 to 1, which is the probability of getting that random variable. So the probability of getting 0 heads is right here. There's 1/4 chance. The probability of getting 1 head, there were 2 of those, right? 2 of those. And the probability of just getting 2 heads was a 1/4 chance. The probability distribution give information about the long-run behavior of the variable. That is, probabilities are relative frequencies. For example, the probability that x equals 2 is 0.25. Then after many observations of x, the x equals 2 value will occur about 25% of the time on average. That's huge, especially the way it's worded, okay? The mean value x, denoted mu, describes where the probability distribution of x is centered. So in this case, it's centered right here. Okay, so let's look at some examples. Let x equal the number of license plates on a randomly selected car. So you could have 0 license plates, 1 license plate, or 2 license plates on a car, right? They don't have any, they're totally incompliant with the law, they've got 1 in the front or 1 in the back, or they've got both, 1 in the front and 1 in the back. Okay, and here's the probability. 5% that they don't have any, 25% that they have 1, 70% chance that they have 2. Notice that adds up to 1 or 100% chance. Okay, and how would we figure that out? Well, there is a 0, we have 0 license plates at 5% chance, plus 1 license plate, there's a 25% chance of that, plus 2 license plates, there's a 70% chance of that, and that gives us an average of 1.65 plates. Okay. Thus, to find the mean of a discrete random variable, multiply each x value times the probability and add them up. So here is the formula for what I just did above. Okay. The term expected value, or E of x, is sometimes used in place of the word mean, because it really is what we would expect to see. The expected mean value will not necessarily be equal to one of the values in the distribution. Instead, we interpret the expected value as a long-term average. For example, if we were to select many cars, we would expect that there would be 1.65 license plates per car on average. So let's say we took 100 cars, because then that makes the probabilities easy. Okay, then the average number of license plates for the 100 cars would be 0 times 5 out of 100, because we expect 5% of the cars to have 0 license plates, which would be 5 out of the 100 cars. And then it would be 25 out of 100, because if it was 25%, we would expect 25 out of the 100 cars to have 1 license plate, and 70 out of 100, because we would expect 70 out of 100 cars to have 2 license plates, which you can see here simplifies to this numerator and this denominator, or again 1.65 license plates. So it's a long run average. Suppose I ask you to play a betting game with me. You bet $5, and if you draw an ace of hearts, I will pay you $100. If you get any other ace, I will pay you $10, and if you get any other heart, I will give you your money back. If you get any other card, I will keep your money. So this is what you would do if you were betting. Okay, you would want to find what you would expect to get if you played the game to see if you should play. So to do it, you create a probability model for the amount that you will win. You start by thinking, okay, let's define the variable. X is the amount won. Okay, and so we'll list all of the amounts you could win here, the situation that would cause that, and then the probability of getting that situation. And notice that I also put the take-home amount. That's a different way to look at it, because if you pay $5 to play, if you win $100, you take home $95. So I'm not really going to use this column, but it's just another way to look at it. You'd get a different if you made X the take-home amount, you could do the same thing and figure out the probability of that, and it would give you the same idea. So if you can see what I did, you could win $100. Okay, if you got an ace of hearts. You could win $10 if you got any of the other aces. $5 if you get a heart except the ace of hearts, then 0 for all other cards. Well, and I'm going to unhighlight those. The probability of getting an ace of hearts, there are 52 cards, and there's 1 of ace of hearts, so 1 out of 52. The probability of getting any of the other aces, well, there are 3 other aces, so 3 out of 52. A heart, except the ace of hearts, well, there are 13 hearts in a deck, So except the ace of hearts, that would be 12 out of 52. And all other cards, if you added up 12 plus 3 plus 1 and subtracted that from 52, you would get 36 out of 52. So these are the probabilities of getting these 4 situations. Okay, and now we want to find the expected value using that. So we're going to use our formula and find the expected value. So we take our x, 100, times the probability of getting it, and add it to our next x, or our next random variable, in this 10, plus the probability of getting a 10, or times the probability of getting a 10, plus the next x, which is 5, times the probability of getting a 5, and then 0 times the probability of getting 0. And you crunch that, and if you play this game, on average, you would expect to win $3.65. Well, you pay $5 to play. So is it a smart idea to play this game? No. Should you play? No. You're going to lose money. Even if you won $3.65, you're going to lose money. You should not play this game. Now that we know we can find out where the distribution of a random variable centered, we would also like to know how far the values are from the center on average. This, of course, is the standard deviation. Using the license plate distribution from earlier, if we had a sample of 100 cars, we would expect 5 zeros, 25 ones, and 70 twos. That means 5 cars would have 0 license plate, 25 cars would have 1 license plate, and 70 would have 2 license plates. Okay, so we know that on average that's 1.65 plates, and so we're going to use the standard deviation formula. Plug it in. Okay, so we'd expect 5 zeros, so 0 minus the average squared, that's this part. And I just went ahead and divided them all by 100, so that's the n. 0 minus average squared, and that's going to happen 5 times. So I would do that 5 times. I'd add them up 5 times. And then I would have 1 minus the average squared. I would have that 25 times because we'd expect that on 25 cars. And 2 minus the average squared, we'd have that 70 times. So you could do that. But of course, you could use what you know about multiplication and have that just be 1 minus the average squared times 5, because it happened 5 times. Or sorry, 0 minus the average squared. 1 minus the average squared times 25, because it happened 25 times. And 2 minus the average squared times 70, because it happened 70 times. And if you go ahead and simplify that, notice that this 0.5, or this 5 divided by 100 is 0.05. And the 25 divided by 100 is 0.25. 70 divided by 100 is 0.70. So we can simplify it like that. And we'd get a standard deviation of 0.572 license plates. So on average, the number of license plates on a car will be 0.57 from the mean value of 1.65. That's a good way to say it. Note, I divided by n instead of n minus 1 because we're not doing a sample. Okay, there's no uncertainty about the values of this distribution. We know exactly what's happening and all of their probabilities. And if you notice, this formula right here was doing this. It was the sum of every value minus the average squared times the probability of it happening. So when you simplified from dividing by 100, because of this formula, it turns into this. So let me go ahead and read this again. Note, it is calculated in much the same way as the standard deviation of a data set, except that we weigh each value with its probability, since the values that show up more often should have more influence on the calculation. Also, you could square that and get the variance. Let's find and interpret the standard deviation for the betting game from earlier. Well, I'm going to go ahead and just show you this. Okay, the betting game had an average of 3.65. So we're going to use our formula, plug it in, and we would find on average the player will win $3.65 plus or minus $13.80. The rest of this we will do in class.